Hello everyone. Today our case study will be about waves. So let's get into it. So our objectives are to answer the following questions. What are waves? How does wind form waves? Then we're going to have a discussion about how and why waves break, and then apply this knowledge for tsunamis. So the first thing we want to answer is, what exactly is a wave? So a wave is actually a movement of energy, not fluid itself. As you can see here on the figure on the right, the little circles with the arrows show the movement of a particular particle of water as a wave passes through it. So depending on where that particle is, whether it's kind of near the top of the water or the bottom of the water, it's going to rotate with a larger or smaller radius. And there's also different kinds of waves. So there's capillary waves where the restoring force is surface tension, and this is usually for wavelengths of less than 1.7 millimeters. And then there's gravity waves where the restoring force is, like the name says, gravity itself, and that's for waves that are larger than 1.7 millimeters. Next, we want to ask, how exactly do waves form? So wind transfers energy via form and skin friction drag to create waves. So it's all basically a transfer of energy through drag. And so this is a function of three things. First, wind velocity. Second is fetch, which is kind of a unique concept, but it's the distance over which wind can blow uninterrupted. And the last thing is duration. So obviously, if you can have your wind blowing for a longer period of time, even if it's slower, you can transfer more energy. Now let's really get into the math to determine how much energy we can transfer from the wind into these waves themselves. So one thing that's really different from the flows that we've previously looked at, like Couette and Poiseuille flow, is we've only really considered smooth surfaces in between those flows. Unfortunately, waves are inherently rough, they're inherently jagged, and as they get those smaller wavelengths and more rough, the way that wind interacts with them changes. So we can kind of see this demonstrated on the figure on the right, where as the wavelength decreases, you can see how the wind starts to form kind of these eddies, or they start just like skipping on top of the peaks of the wave. And so we need a way to relate this so that we have a good estimate of really how much energy we're imparting from the wind into the wave. So one way we can do this is to simply determine a coefficient. So this is called the transfer coefficient for momentum. Basically, it's going to tell us out of how much energy is coming from the wind, how much is really going to get into the wave itself because of the roughness. So one analysis technique to do this is called the bulk drag coefficient technique. So this was created by Smith and Bank. They basically just went out into the ocean and they measured the wind speed about 10 meters above the surface, and then they compared that to the size of the waves that they were reading, and they came up with a linear relationship between the transfer coefficient for momentum, or CD, and the wind speed. So this is a really easy technique. It's great for modeling. It's great for getting a general idea of what's going on, but it's also important to note the limitations. So they themselves, in their write-up in their report, noted that, hey, there might have been some varying conditions during data collection. For example, maybe the wind speed wasn't exactly constant at all times, and they might have some different directions of wind speed that interfered with their data. They also say that their estimate is probably not great in extreme conditions. Again, they just went into some mild, calm waters where the wind speed range was 2.5 to 21 meters per second. So nothing like an extreme hurricane sort of example. So now that we've set our limitations, it's good to note that, hey, it's going to give us a nice general idea, and for the purposes of our case study, this is probably okay. So now let's go ahead and try an example and try to figure out how high the wave will be. So given that the wind blowing is 10 meters per second, the fetch is also 10 meters, and the wind is blowing uniformly for 3 seconds, how high will the wave be? It's important to note, so the wind is blowing at 10 meters per second. In this case, we're going to assume that that speed is 10 meters above the surface, and then the surface of the water at that instant when it starts blowing is not moving at all, so it's stationary. And let's also assume that the period of the wave that's going to be formed is 2 pi. And we have the density of seawater, so let's assume that this is out in the ocean, is 1,029 kilograms per meters cubed. So go ahead and pause the video if you want to try, and I'll be back if you want to work it out together. So now let's go ahead and work it out together. So we know that first we can figure out what the transfer coefficient of momentum is. So given that the average wind speed is 10 meters per second, we can determine that CD is 1.29 times 10 to the negative 3. Note that this is unitless, it's just a coefficient. From there, using the equation on the previous slide, we can determine the stress imparted from the wind on the water, and that comes out to 132 pascals. Then, knowing the fetch, we can find the total amount of force put onto the water, and that comes out to around 1,300 newtons. And then we can determine work. So work is just force times distance. And it's important to note that all of these are like shear stresses and shear forces because the wind is blowing horizontally onto the water. So we have force times distance, which is just going to be the force that we calculated on the previous line. And then we will find the distance by incorporating how fast the wind is blowing for how long. And so putting all that together, we have a total energy of 39.6 kilojoules. So we've basically determined how much energy we are putting into the water at this point. And so now we need to find how high that total wave height is going to be. And we can do that by basically figuring out an expression for how much water we're going to lift. So we can do that with our handy dandy little integral over here, and we can figure out that the energy required, or the energy in that wave with a period of 2 pi comes out to 2 rho gh. Then we can solve for h, substituting in the energy that we've already solved for and the density and gravity, and we can find that the height of the wave is a little bit under 2 meters. Alright, so quiz time. Given a wave is 10 feet high and has a period of pi over 2, the wind velocity was 15 meters per second and had a fetch of 1 meter, how long did the wind blow to make this wave? So go ahead and try it by yourself, and then we'll come back and solve it together. Alright, so given a 10-foot tall wave with period pi over 2, let's first off convert 10 feet into meters, so that comes out to about 3 meters. We want to first calculate the energy needed to make that wave with a period of pi over 2. So we do that again with a handy dandy little integral, and we're using like a sine wave basically. And so that comes out to around 9,000 joules. Let's also now find the coefficient for momentum given 15 meters per second. This comes out to 1.62 times 10 to the negative 3, again unitless. We can then find the stress imparted from the wind on the water. That comes out to around 375 pascals. Then we can find the total force, which since fetch is just a meter, is just 375 newtons. And then we can find the work done on the water, and we know that is equal to 9,000 joules, and we can solve then for time. And so that comes out to about 1.6 seconds, which kind of makes sense because we had similar values last time for our wave that was created. It was about 3 seconds. In this case, we had a slightly faster wind speed and a much smaller period. So it makes sense that we have around a similar number, but it's still a little bit smaller. So next up for discussion is we want to talk about, why do waves break? So there's this thing called wave shoaling, and it's basically shoreline interaction and decreasing depth. Essentially just slows down the bottom of the wave while the time between the peaks, or like the wavelength, stays constant. So as that happens, basically the wave height increases because it wants to conserve energy because it's being slowed down, but it's still kind of speeding up on top. So it starts increasing its wave height while the speed of the overall wave is decreasing. And then eventually the top of the wave is just moving faster than the bottom of the wave, and there's an increase of surface drag coefficient, and that basically causes the top of the wave to fall over itself. So one little question we can have is, how could waves break without reaching the shore? Basically, if you're out in the, even if you're out in the open ocean and you have a strong enough gust of wind that rapidly accelerates the top of the wave way more than the bottom of the wave can catch up, it will also break. So basically, it's kind of this interaction of, hey, the top of the wave is moving faster than the bottom of the wave, and that's why it falls. So next we have a little bit more of an intuition quiz. What can we determine about that transfer coefficient of momentum in extreme conditions? So first, let's note that there is a maximum height to waves due to the energy balance with waves breaking. So basically, imagine like a really big lake. There's only so much energy that you can put into that body of water, and it's basically balanced out by when waves break, they release that energy that's trapped by holding up that water high in the wave. So there's this energy balance between having waves and having waves break. So to maintain this energy equilibrium in high wind conditions, how must this relationship with this transfer coefficient behave? So basically we have A, it plateaus and then decreases, B, it increases linearly, and C, it just reaches some constant and it just stays there. So take a couple minutes, try to think it out, and we'll come back and work it out together. So the answer is A. At first, the higher wind speed will be able to cause waves to break, so the constant won't change. So basically, as that wind speed increases, more and more waves are going to accelerate their top over their bottom and just start to break, and it will keep this energy balance going. But as time continues, waves aren't going to be able to break more frequently, right? There's only so many waves that are going to be tall enough that this higher wind speed is going to cause them to break. So while more and more energy goes into the system, in the form of more and more wind speed, the coefficient is going to need to decrease just to maintain that energy equilibrium. So now let's apply some of this knowledge that we've learned towards tsunamis. So just kind of two phenomena to note, I guess, in the wave field is that the deeper the sea, the smaller the wavelength, and as wavelength decreases, height increases. So basically, do we need to be concerned about a tsunami in the Great Lakes? For kind of perspective, the average depth of Lake Superior, which is the largest lake in the Great Lakes, is 147 meters, and the average depth of the Pacific Ocean is 4,000 meters. So if we think about it, so we know that the deeper the sea, the smaller the wavelength, and as the wavelength decreases, the height increases. So we don't really need to be concerned about getting a tsunami in Ohio or Michigan because the average depth of those lakes is pretty shallow. So the height of any waves produced shouldn't be too big versus the Pacific Ocean. It's pretty deep, so it's going to cause a lot larger waves, and we can just, this makes sense intuitively with various things we've experienced in our lifetimes. We don't really get too concerned about getting a tsunami from Lake Erie or Lake Superior. So finally, to wrap it up and just go over some of the things that we've learned in this case study, we learned about what are waves exactly, how the wind forms waves, how waves break, and we've applied some of that knowledge for the potential for tsunamis. Thank you, and have a great rest of your day.